morning, class, and welcome to another lecture in the Sustainable Energy Technology course. So today we will discuss a few solved problems to help you gain a grasp, give a grasp of the ideas behind how much pollution is being emitted by different types of fossil fuels. So in a few worked out examples that we will go over, we will see how much a typical coal power plant or a typical natural gas power plant emits in generating the amount of electricity that it generates over a year, say, and how you can calculate those values. Okay. So, before we begin the discussion, let's look at a few quantitative estimates of how much energy is released when a hydrocarbon like coal, natural gas, etc. is burnt. Alright. So if you look at the elements that are present, yes. So the main elements in hydrocarbons are carbon and hydrogen. Alright. So what else might be present? There might be other pollutants like ash, which does not burn, but also coal may contain a little bit of sulfur, which also when it burns produces some amount of energy. So the main fuel elements present are hydrogen, H, and carbon, C, and sulfur, S. Correct? And what is the the atomic weight of these elements? Atomic mass. For hydrogen it's 1, for carbon it's 12, and for sulfur it's 32. So that's the weight of one atom of sulfur, one atom of carbon, and one atom of hydrogen. Now, the next column is heat released on oxidation. It is how much heat is being released by each of these elements when they are completely oxidized. So for carbon, it is, for hydrogen, it is 119,950. So it's 119,950 kilojoules per kg. Alright, so hydrogen releases more than 119,950 kilojoules of heat when 1 kg of hydrogen is burnt. For carbon, it releases 32,770 kilojoules per kg, and sulfur, it releases 9,163 kilojoules per kg. And what is being formed when hydrogen is completely burnt? The oxidized product is water, H2O, CO2, carbon dioxide, and SO2, sulfur dioxide. Alright. The other important consideration is air contains approximately 21% oxygen and 79% nitrogen by volume. And molecular weight of oxygen is 32, 16 into 2, and nitrogen is 28, 14 into 2. Alright. So 1 mole of oxygen molecular oxygen, it weighs 32 grams, and 1 mole of molecular nitrogen weighs 28 grams. Okay. So based on these data, the other important molecular weights are molecular weight of CO2 is 44, molecular weight of SO2 is 64, and also molecular weight of NO. So nitric oxide is also formed to some extent due to the oxidation of nitrogen, is 30. So 14 plus 16, 30. O2 is 32 plus 12, 44. 32 plus 32, 64. So these molecular weights are also important parameters that you need to remember. So if you do the calculations, we can say how much oxygen is needed to burn 1 kg of each of these elements that is typically present in fuel. So if you look at element, so the element is C, 1 kg. So how much oxygen is needed to burn 1 kg of carbon? Alright. So 1 kg of carbon reacts with 32 kgs of oxygen to produce CO2, 44 kgs, right? The reaction is basically C plus O2 going to CO2. So kg of O2 needed per kg of carbon to be burned is 2.67. How do we get this number? This is 32, this is 12. So 32 by 12 is 2.67. Now, air contains 21 moles of oxygen and 79 moles of nitrogen. So we can convert this into kg of air needed. How much air is required to supply 2.67 kgs of oxygen? So kg of air needed is 11.5. Okay. How did we get this? See, 79 moles, so 79 moles of nitrogen and 21 moles of oxygen produces 100 moles of air. So 100 moles of air contains 21 moles of oxygen. So 2.67 moles of air is moles of oxygen is contained in how many moles of air? And you multiply it by the molecular weight of air to get the kgs of air needed to burn 1 kg of carbon. This can also be given in terms of volume of air or meter cube of air needed. Because air is a gas, a certain mass of air at 1 atmosphere will occupy a certain volume because of ideal gas law. So that will be 9.7 meter cube. So 1 kg of carbon requires 2.67 kg of oxygen to completely burn, which is contained in 11.5 kgs of air or 9.7 meter cube of air. Similar thing can be done for hydrogen. 1 kg of hydrogen. Okay. So here the reaction is H2 plus half O2 goes to H2. So H2 is 2 kgs because elemental hydrogen is 1 kg and half O2 is 8. So 2 kgs of hydrogen, 2 moles of hydrogen combines with 8 moles of oxygen. Correct. Or half, 2 kgs of hydrogen, correct, combines with 8 kgs of oxygen because molecular weight of oxygen is I am making a mistake. Sorry about that. Molecular weight of oxygen is 32. 32 by 2 is 16. So 16 kgs. Okay. So 1 kg of hydrogen reacts with 8 kgs of oxygen. Correct. So this is 8. So 1 kg of hydrogen requires 8 kg of oxygen to completely burn, which is present in 34.33 kgs of air, which is again 28.97 meter cube of air. Similarly, if you go to sulfur, you have S plus O2 going to SO2. Here the relationship is straightforward. 1 kg of sulfur combines with 1 kg of oxygen, because this is also 32, this is also 32, and this is 4.3 kgs of air. So here you get the straightforward relation that 4.3 kgs of air contains 1 kg of oxygen. And you will see this ratio also here, 34.33 by 8 or 11.5 by 2.6. And this is equal to 3.63 meter cubes of air. So what we are seeing here is this gives you the heat released when burning a kg of each of these elements present in fuel, right? This gives you the molecular weight of the individual gaseous products and reactants, and this gives how many kg of air or oxygen or meter cube of air is needed to burn these elements completely. So next we will collect all of these ideas together. First is we want to find the heat released by a fuel. Fine. So typically the fuel will have some amount of carbon, some amount of hydrogen, some amount of oxygen, some amount of sulfur, and maybe some amount of nitrogen. Alright. Carbon and hydrogen are the main product contents of a fuel. Oxygen, sulfur, nitrogen are smaller amounts that may be present in smaller amounts. Alright. Now, what we want to find is the total heat released by a fuel which contains a certain kg of carbon, certain kgs of hydrogen, certain kgs of oxygen, certain kgs of sulfur, and certain kgs of nitrogen. Alright. Now, while nitrogen burns with oxygen to produce nitric oxide, that reaction does not release any heat. So nitrogen and oxygen oxidizing to produce NO does not add any heat to the combustion process, so we can neglect that. So what we are left with is these three. Now of this, oxygen of course will not produce any heat itself. Okay. And if in a fuel oxygen is present to some extent, it will be present in bound form in terms of water vapor. Okay. So for coal particularly, for coal with certain C is to H is to O is to S is to N mass ratio, the heat released is given by Q equal to 32770 into mass of carbon present. So MC is the mass of carbon present in a certain amount of coal. Alright. And 32770, what is that? That is the amount of heat released per kg of carbon. Alright. Now similarly you would think that the amount of hydrogen present, you can multiply straightforwardly with this one to get the amount of heat released from the hydrogen that is present in your coal. However, this is not true because some amount of oxygen is also present. And what this typically means when you do an elemental analysis, that the coal contains a lot of moisture. Okay. So as we discussed, some of the coals will have a lot of moisture in them. So a part of the coal mass is basically H2O. Okay, only the part of hydrogen which is not present as part of moisture in H2O is generating heat, because water will simply evaporate. It will not burn, right? Now what is H2O? H2O is water which contains 2 kg of hydrogen per 16 kg of oxygen, correct? So suppose you have in a coal certain mass of oxygen, all right? So that mass of oxygen comes entirely from water. So that water contains 2 kg of hydrogen per 16 kg of oxygen, correct? So based on that, you can find out how much hydrogen is present in bound form with water, which will not contribute to any heat that is being generated during the combustion process. So based on that analysis, we can say this is the heat released by burning 1 kg of hydrogen that is unbounded to water, to mass of hydrogen minus 1/8 of the mass of oxygen. So this is mass of H bound in H2. So suppose you had 100 kgs of oxygen present. Okay. Now for every 16 kgs of oxygen, 2 kgs of hydrogen will be present in water form. So in 100 kgs, it will be 100 by 16 into 2, or 100 by 8. So MO by 8. This is what this expression is giving. And finally, you have the sulfur content. So 9163 into S. So this is the total mass present. This is mass of sulfur. So this is the total heat released when you burn a certain amount of coal which contains mc kgs of carbon, mh kgs of hydrogen, mo kgs of oxygen, and ms kgs of sulfur. Right? Now, what is the amount of oxygen needed to burn this kgs of coal? Alright. Now this is the total mass of carbon. Now 1 kg of carbon requires 2.67 kgs of oxygen, or 11.5 kgs of air. So you multiply this by 11.5 to get the amount of oxygen needed to burn carbon. Similarly here, the 1 kg of unreacted hydrogen requires 34.33 kgs of air. So you multiply this by 34.33 and multiply ms by 4.3 to get the total amount of air needed. So amount of air needed to fully burn coal, m air, is equals to 11.5 into mc plus 34.33 into mh minus mo by 8 plus 4.3 into ms. So this is the total amount of air needed to fully burn that coal, which contains this many more mass of kgs of carbon, this many kgs of hydrogen, this many kgs of oxygen, and this many kgs of sulfur. Finally, amount of CO2 emitted, mCO2, is 44 by 12 mc, because 44 kg of CO2 is emitted per 12 kg of carbon. So this is a straightforward relationship. Fine. Finally, we can also define something like, if thermal efficiency of a power plant is eta, which is equals to the net useful work output by the net heat input, W out by Q dot. And here this W dot out is the electric power production in kilowatts, and Q dot is the heat generation also in kilowatts. Alright. So this is the heat generated for a given mass of coal. Okay, now the power plant is continuously consuming coal to generate heat. Okay, so there is a certain amount consumption rate of coal. So say 100 kgs per second of coal is being consumed. Okay. From there, so every second 100 kg is being consumed, and say 1 kg of coal contains this many grams of carbon, this many grams of hydrogen, etc., etc. So you can get what is the heat generated per kg of coal. Then you multiply by 100 and you will get the heat generated per second in your power plant. And this is your heat generation rate in your power plant. And this is the electric power output. Then the efficiency is the ratio of the net useful energy output, which is electric power, by the net heat input, which is the heat that is being generated. So these thermal efficiency values are also often given. So now that all of this is known, let us see how we can use these to create an example where we can solve the amount of pollution that is being generated by a certain power. Okay.